We are driving a later model JK with an LS3. It would be nice if I had a nickel for every time somebody called me and said, I'm putting an LS3 in my JK, and it turns out they have an L94 or an LC9. LS3 has kind of become the generic term for an LS. But the LS3 engine is actually very different than most of the other LSs. So they don't have active fuel management, they don't have variable valve timing, and most importantly, they were manual transmission vehicles, where almost all the other LSs were automatics. But they were basically put into high-performance SS vehicles. So we have to kind of put the LS3 in a different category than everything else. Now, the engine has become very popular because it is simple, it is a track engine, it's used in pretty much all the racing events, whether it's circle track or off-road, Baja, King of the Hammers. Some variant of the LS3 almost always wins. Since there is so much confusion about origin of engines, and this can be important when you're registering your vehicle, and depending on what your jurisdiction requires, some areas, now we're all under US EPA rules. That covers all 50 states. But the feds don't enforce inspections in all jurisdictions. It would be physically impossible or too costly. So every jurisdiction has the right to do their own inspection, but we're still all under federal rules. So some areas like California, Colorado are extremely strict, and other areas like down south aren't. Bottom line is, in some areas they do check the origin of the components, including the engine. And the transmission is also part of the inspection process, or the powertrain. So if you take an L94 or a 5.3 and you put in a manual transmission, technically that's not compliant. You have to stay with the original donor configuration that was approved by the US EPA or the ARB. So as usual, let me ramble a bit and get some of this out of my head. And I'm going to talk in generalities here because there's always that oddball or one-off instance, or some guy with no life living in a basement says, oh, there was a one-off engine in 1992 that was built for a special purpose need. I'm just talking about generalities here. The V8 engines have been around a long time. The Liberty engines for the World War I aircrafts, and there was many others. There was other configurations too, including V12s, V16s, but here's the deal. Most of those engines were put in the high-end vehicles, Duesenbergs, Cadillacs. My grandfather actually had a V16 Cadillac. Very costly, a lot of hand labor to build these. When Ford introduced the flathead V8, that really did bring the V8 to mass production. The technology, though, was really not that much greater than what they had at the time in the straight 6s and the straight 8s. They were still using a flathead design, which meant the valves were in the block. So while performance was good, it was limited compared to what we have today. The oiling systems were lower pressure, the fuels weren't as good of a grade. It was a great engine for that time in the 1930s, but really the high performance V8 required a couple of additional steps before it could become popular to the masses. One was the manufacturing cost, and Ford had spent a ton of money in engineering trying to figure out how to make the core castings for the early flathead V8. When thin wall core casting and casting technology increased in the 1950s, that allowed Chevrolet and Ford to make some economical core castings. I do believe the Chevrolet engine got the core castings down to about 22, maybe 23, right in there. So it tells you how complex the V8 is. And the bottom line is the cost of casting the block and finishing it, machining it, was a lot of work. So at the same time, machine tool technology was coming around for mass production. The second part is the fuel. The grade of the fuel really kept our compression ratios low. So 7-to-1, 8-to-1 was considered normal or high compression in the day. But in the 50s, after the war, the US, one of the reasons the P-51 outperformed a lot of the other fighters, including some of the German fighters that were considered superior, wasn't so much the engine or the airframe, while the P-51 was very advanced, but the fuel. The Americans were able to run a lot more boost, a lot more manifold pressure than the Germans, because we had fuel that had anti-knock. It was almost a top secret, or I will say it was a top secret technology that we had. At the end of the war, the Germans did start to produce some synthetic fuels that had higher knock resistance or octane, but really before that, if you look at the 109s, the reason the P-51s could outperform them, a lot of that had to do in the fuel we were running. So this fuel technology distilled down to the public, and in the 50s, higher compression engines started to come about. You remember the Oldsmobile rocket engines, and by the 1960s, of course, we had motors that were over 11.5 to 1. We did that by using great fuel. Today we're using 11.5 to 1 motors like the LT1 through technology, and it's amazing technology by controlling cylinder pressure and direct injection, and a lot of the other technologies that the LT motors have is the reason that we can run such high compression with low-grade fuels. But back in the day, we had to have the high-grade fuels to run the high compression. So in the mid-50s, around 1955, Chevrolet really made a breakthrough. They came out with this thin wall casting technology, small block Chevy engine. It was originally a 262, I believe, and then it quickly moved into a 283, and they ended up going to a lot of other displacements. They went to there was a 302, a 305, a 327, a 350. There was even a 400 small block. So over the years, the small block Chevy just dominated and ruled the engine performance market. It also dominated and ruled racing. And yes, you could be competitive with a Ford or a Chrysler engine, but you were just going to spend a lot more money. One of my favorite engines is a 346 pack I have in an original Trans Am Challenger TA. I used to call it the Giant Killer because it was really faster than most of the big blocks that I had. And that engine really got no recognition. Chrysler didn't do that well on the Trans Am circuit. The AAR CUDA and the Trans Am Challenger were really kind of forgotten. But it's interesting, I just saw a brand new TA Challenger, and they are awesome. They are awesome vehicles, and it's good to see that they're being appreciated finally. But I've got one in my garage, an original 1970. So with this new casting technology, new fuels, V8 engines started to become the norm in American cars. While the Europeans stayed with straight 6s like Jaguar or straight 4s and even a lot of the V6s. Of course, the exotics went to some V12s and V8s like Lamborghini and Ferrari. Because of regulations and other reasons, the Europeans primarily stayed with the smaller displacement engines, where the Americans just kept making their cars bigger, their engines bigger. If they wanted more horsepower, they would just increase the size of the motor. So we would go from a 283 to a 327 to a 350. Then the big block Chevy was introduced in the mid-60s, and there was actually a version of it prior to that, the 409s, but we're not going to talk about the big blocks right now. But we got up to a 454, a 501, and essentially the technology didn't change. We just made the engine bigger to get more horsepower. Most of the other countries couldn't do that. They needed technology to get more horsepower because of rules and regulations. So they went with 4-valve combustion chambers, cloverleaf combustion chambers, dual overhead cams, and other technologies that got horsepower without increasing displacement. Unfortunately, a lot was lost in the transmissions of the day. The manual transmissions were relatively efficient. However, after World War II, when the Hydramatics and other automatic transmissions came out, it was pretty clear that that's what the public wanted. Women and even professional men, they didn't want to stick. So automatic transmissions of the day, they had 2 speeds, 3 speeds, just were not very efficient, and they robbed a lot of the horsepower of the engines of that day. So it became the standard in the muscle car era was a 4 on the floor, a 4-speed manual transmission with a shifter on the floor, like a Muncie or a Hurst. And pretty much through the 60s and early 70s, that's what ruled in the muscle car era. I've got 69 Z28s. I told you I've got the Challenger TA. I got a Hemi Charger and just a bunch of other muscle cars, and they're all manual transmission 4-speeds. But back to the engine, the small block Chevy quickly evolved. In the 1950s, Zora Duntov wanted to make the Corvette more competitive with what was out there in the European market. So he started to pump them up. He put dual quads on a 283, which some argue was the first 1 horsepower per cubic inch engine. Chrysler 300 guys might differ with that, but it was an immensely powerful engine for its size and its weight of the time. There was the Duntov cam, so they were starting to cam these engines in the 50s, and pretty much by the mid-60s, the muscle car revolution was on. John DeLorean pushed and introduced the GTO. He kind of snuck it in under the radar, and what he wanted was basically a smaller chassis, like a Tempest-style chassis with a large engine. That really kicked off the horsepower race. We're not going to get into what happened, but by the early 1970s, insurance companies and liability, of course, killed that. And then in the late 60s, emissions started to become very important with the ARB in California. Ronald Reagan kicked that off. So compression ratio started to drop. Emissions equipment like air pumps, air systems, EGR valves. Well, EGR valves really didn't come out till the mid-70s because they didn't understand NOx at the time. But let's just say the engine started to get choked down, and it was the black era for engine performance. The early 70s all the way through, I'm going to say, the mid 80s. But there was always one constant, and that was the small block Chevy. The small block Chevy, whether you got a 283, a 327, a 350, they were awesome engines. There was the impotent 305 that was introduced in the 70s for emissions. They were lower compression. They put them in vans. They didn't get great economy. They didn't have great power. It was kind of the dark days of the small block Chevy, but it was still a small block Chevy. And you could still put intakes on them and heads and port them and get really good horsepower. So the small block Chevy became the Lego building block for the muscle car era. And it was used by everybody. When I started doing engine conversions in the late 1970s, we were putting small block Chevys in Vegas, in Pintos, in Toyotas. You name the chassis and we were putting them in. Big block Chevy was a great engine, but it was also large and heavy. They called it the semi-Hemi because the valves are slightly canted. It is not a true Hemi, but big block Chevys really had a lot of torque and power, mainly because of the displacement they were running. So we're going to call the first generation of small block from about 1955 to the early 1990s or the late 1980s. In the late 1980s, GM was really pushing performance with their Trans Ams, the IROC Camaros and Z28s. They went to a tune port intake system, which I thought was really, really good. When we went to fuel injection, it solved a lot of problems, especially for off-roaders, because running a carburetor off-road is really a pain. Whether you had a throttle body or a tune port, you had a lot of advantages. Cold start was better, economy increased. The benefit of the tune port over, let's say, a throttle body is when you have a throttle body, it's still putting fuel into the intake that then needs to be distributed through a manifold like a carburetor, where port injection puts that fuel right behind the intake valve, and we know that direct injection now puts it right into the chamber. So the closer you can get it into the chamber, the better. But the technology really improved in the 1980s. They were cleaning up emissions and they were improving the engines. But unfortunately, it was kind of like lipstick on a pig, because here we have an engine that was basically designed in the 1950s, trying to be modernized for the 1980s. And they were trying to keep interchangeability. So you really couldn't make major changes, like the block mounting pretty much stayed the same all the way through production. The architecture of the engine stayed pretty much the same. But the Generation 2 small block had some subtle but significant changes. They reversed the cooling flow so that the heads got the water first. That helped keep the heads cool and the combustion chambers cool, so they could raise compression and get more power and economy just by changing the cooling system. And the cooling system is really an integral part of engine performance, and I am pretty amazed at how well the LTs cool. Even with the compression they have, they seem to run cooler than everything else out there. They also changed the block so they could run roller lifters. They machined it differently. They started to run roller rockers. They were trying to reduce friction. They added serpentine belt systems to reduce friction, but again, it was lipstick on a pig. They were getting small gains and small improvements. But I will say that in the late 80s and early 90s, the small blocks really were good, reliable engines, and they got pretty decent economy compared to their earlier counterparts. However, what was coming was really going to change the game, and that was the Generation 3 LS. In the late 1990s, GM decided we have to get a more modern architecture, an engine that can take advantage of the technology we have today. So one was going to aluminum construction, and they stayed with iron construction for the lower cost base engines and some of the heavy duty truck engines, but pretty much the LSs went over to aluminum construction, aluminum heads and aluminum blocks. Remember, the earlier small blocks were cast iron heads and cast iron blocks. So right there we lost a lot of weight. They skirted the block, went to a 6-bolt main, really made the block strong, and they needed to do that because with the new technology, we were nearly doubling the horsepower of these engines. Now I want to mention briefly, in the mid-1990s, in 1996, when the feds introduced OBD2, Onboard Diagnostics 2, and that's another video, they did require sequential fuel injection, so misfire detection became important. Top dead center sensors were added into the distributors. That was one step better than the port injection and the throttle bodies.